can share. But I need to also send a request to share. I need to.
Were you already? Oh,
No,
I
I need to.
Okay, 1 second. Okay, everyone. Thank you and welcome everyone in live and welcome everyone online. This is our first digital cafe of the term, and this is our first digital cafe in person. So we're thinking of calling it Tech Tea Time Talks now. All right, maybe I'm gonna push for that name change. You like it?
Yeah.
Okay, great. Because it's tea time. We thought there were a lot of things going on around free hour. It's not really free, so we decided to try a new time. And people like to come to talks in the afternoon when things are going slow and see what's going on. So I think this is a great new venue for this event, for this series. And Baole has been our first speaker. So if you didn't know, Baole is a professor of mathematics here in the NYIT. He and I joined together in 2022, the fall of 2022. I remember very well. And Baole is coming to us from a PhD in Texas most recently, a postdoc at Texas most recently. Before that, he was at University of Michigan and also at the University of New Hampshire. And so Baole's got a number of recent grants recently. Most recently, very proud of him, he's got a NSF award for $250,000. So good for him for the next couple of years. And I think he's going to be telling us some about the stuff he's been working on and going to be doing in that project. So Baole, take it away. Thank you.
Okay, thank you so much for introduction, William. Thank you for coming to this presentation. Today I will talk about one project of my research, asymptotic transport in strongly nonlinear thermal convection. This is the joint work with David Gluskin from University of Victoria and Greg Cheney from University of New Hampshire. Okay, so this talk contains 3 parts. Okay, at the beginning, since many of you are students, I will spend some time on the background and motivation of my research. Probably this is the most important part for you. And then I will talk about some, the computational method and the theory we used to perform this research. And finally, I will talk about a research based on curriculum we built for the applied computational mathematics major. Okay. One objective of this talk is I just want to show you how the concept learned from the applied computational math major can be used to solve some challenges in the sum. Okay. All right, the background. So thermal convection, it's a very common, very common in the nature and in the industry. Okay, so you can see on the top left, you can see kitchen. When you hit the saucepan, the water from the below, you can see it's heated from below, right? So the hot water, the density is lower, so it will rise. Okay, for the on the top of this saucepan, you see the temperature of the water is relatively low. The cold water will sink. So this rise, this sink. This will induce a convective motion. Okay, this process will significantly increase the rate of the heat change. In the cooking. Okay, that's our kitchen. So let's look at its mental convection. So for our Earth, the core of our Earth is the temperature is very high, right? It's much higher than the temperature on the surface. So you have something is heated from below, so you will induce some convective motion. This is called the mental convection. Actually, this process is the primary mechanism for the plate tectonics. Okay, so which will lead to for example, the mountain formation, the earthquake, and some the shape of the Earth's surface. Okay, let's look at the sun. Near the surface of the sun, there is a convection zone. You can see that. Okay, this zone, this layer is very important for the energy transport from the sun's interior to the sun's surface. Okay. All right. So things is complicated, right? So to understand the mechanism of the heat transport, people usually study a simplified setting, which is called Rayleigh-Bénard convection. Okay. In this setup, the fluid layer is heated from below and cooled from above. Okay. In the following of my talk, I will use this simplified scenario to discuss some computations and perform some analysis. Okay. So here is a Rayleigh-Bénard convection, Rayleigh-Bénard scenario. So you can see there. I'm considering a 2D layer. So between these two walls is the fluid layer. Okay, think about that water or gas. Okay, so the fluid layer is heated from below. So the non-dimensional temperature is 1 at the below at the lower wall. At the upper wall, the temperature is 0. Okay, so for the velocity, so if you have two walls, this no penetration, right? The flow cannot pass through the wall. So the vertical velocity vanishes at the top and the bottom. Vertical velocity W is 0. Okay. For the horizontal velocity, there are two types of boundary conditions. The first type is we call that no slip boundary condition. Okay, no slip, it means the tangent velocity is equal to 0 at the wall. Okay, this is pretty common in the experiments, the laboratory experiments. Okay, the second type of boundary condition, we call that the stress-free. There's no shear at the wall. Okay, so this boundary condition is pretty common for example, in the ocean, the surface of the ocean, and in the surface of the sun. Okay, we use a stress-free boundary condition in that cases.
So you're saying in some cases there's no tangential velocity at all, but in some cases there is tangential velocity, but only in one direction.
Okay. Since in the laboratory experiments, when you hit the wall, the flow is 0 at the wall. Okay, that's a no slip boundary condition. But in nature, imagine the ocean, the surface of the ocean, and there is no shear instead of there is no velocity, Okay. All right. So here is the dominant equations. Okay, you can see this is a group of nonlinear PDEs. Okay, so you can see this is on the top. This is the advection diffusion equation. This equation is coupled with the Navier-Stokes equation. I know many of you are from the mechanical engineering, so you may have learned the fluid dynamics. This the famous Navier-Stokes equation, right? Okay. So for the 2D system, we normalize the system using these parameters. Then you can see we have 3 control parameters. Okay, the first parameter is called the Rayleigh number. This is the driving stress. Okay, this number is proportional to the temperature difference across a layer. If you have a high temperature difference, this value is higher. Okay. The second parameter is called the Prandtl number, which is the ratio of the kinetic viscosity to the thermal diffusivity. Okay. The last one, that's a geometry parameter. This is called the aspect ratio. That's a domain aspect ratio. Okay. When gamma is 1, that's a unit box. Okay. When gamma is small, that's the domain is very thin. Okay. The quantity we are interested in is the normalized heat flux. We call that the Newton number. So this here, the normalized flux is the ratio of the total flux to the conduction flux. Okay. The challenging for this problem is we need to find how the heat flux, the Newton number, vary as a function of the Rayleigh number and Prandtl number and the domain aspect ratio. That's a challenge. Okay. All right. So for this system, the thermal convection, the conduction state here, T is the linear function of the z direction, and the velocity is 0. This is the conduction for there's no motion. Okay. This state always exists for any parameters, for any Rayleigh number, Prandtl number, gamma. Okay. However, when a real number is beyond some critical value, for example, beyond the nearly 2000, some instability happens. Okay, so here I show some examples. In this here we perform some simulation at real number 2 times 10 to the 6. Okay, 2 times 10 to the 6, that's higher than this critical value. So right, so the conduction state will be unstable. So we initialize the flow field using the conduction state, and then we give it some random perturbation. Let's see what happens. Okay, you will see some instability happens. Okay, the flow transition from the conduction state to some convective rho solution. Okay, this animation is made by our mathematics major Kyle Steven. Okay, by the way, Kyle is a undergraduate student from my PD class, numerical analysis class, and the mathematical fluid dynamics class. Okay. All right. So here, when the real number is low, its conduction is stable. But when the above some critical value, the conduction becomes unstable. As you keep increasing the real number, you will see that the flow becomes turbulent. Okay, this is so-called the turbulent convection. Okay, at the large real number regime, you can see that the Newton number, the heat flux, is proportional to some parallel scaling of the real number. So the Newton number is proportional to real number to some power beta. Okay, so I know some of us students, they're curious about the asymptotic transport. What does it mean? So in this talk, the asymptotic transport, it means as real number goes to infinity, what is this parallel scaling? What is the value of the beta? Okay, so it's still an open question. Okay, so what is the value of this asymptotic exponent beta as real number goes to infinity? So why we are interested in the value of beta? This is because in many geophysics settings, the real number is huge. You can see in the deep ocean convection, the real number is about in the order of 10 to the 25. This is far beyond the current computing power. Okay, so you can see, look, this simulation is up to 10 to the 10. If there's no way to go to 10 to the 25. Okay, so if we know the exact value of this beta, we can use this formula to predict the heat transport. At a much higher real number. Okay. All right. To find this, to determine the value of beta, in research, usually you can do theory, right? You can use some theory. You can use some experiments, right? You can set up some experiments. You can set up some numerical simulations. Okay. So so for the theory, there are two famous theories. The first theory is so-called classical theory, which assumes that the transport is dominated by the thermal boundary layer near the wall. Okay, so these three arguments, they are separate arguments. All of them can derive this 1/3 scaling. Okay, the other theory, which is called the Asymptotic theory, they assume that the transport at a large real number, the transport is dominated by the interior. Because at a large real number, the flow is so strong, the thermal diffusivity and connect viscosity could be neglected. Okay, that's their argument. So this theory produced a 1/2 scaling. Okay, so maybe you will say, okay, 1/3, 1/2. It's not. It's just it's the difference is only 1/6, right? But in the geophysics application, remember the real number could be 10 to the 25. That will be a huge difference if you use this different exponent. Okay. All right. So, but for the series, there's many challenges. First of all, you can see this series, they rely on some many assumptions. Okay. they lack the rigorous derivation of the governing equation. Okay, they're not from the governing PD. Okay, they just sometimes it's just argue. Okay, argue and derive something. Okay, that's pretty common in current fluid dynamics. Okay, and secondly, you can see these predictions, they're qualitative prediction. We don't know the coefficients. Okay, most importantly, you can see these two series, they yield different scalings. We don't know which one is good, which one is true as real number goes to infinity. Okay, so one of the current community, they try to roll out one of the other of this series. That's one primary task. Okay, that's a theory. Okay, so we know it's two theory, but we don't know which one is correct. Okay, so besides the theory, you can use the experiments, right? Use the experiment. Most of the experiments were performed in the can. Okay, so here I give you some examples for the famous experiments. However, when the real number it's increased, they have some many challenges. Okay, first of all, the cost is extremely high. Usually it's millions of dollars. Remember, this is 10 years ago, this experiment. Due to the inflation, I don't think you can cover this in 1 million. Okay, currently. Okay. Moreover, these experiments generally they will look at this can. The aspect ratio is about one below 1. So the experiment is affected by the sidewall. Okay. And as real number goes to very large, there are many measurement uncertainties. Okay, so the different groups they have different data. So some group they have 1/3 scaling. Some group they have the data rise. So they think okay the scaling will go to transition to 1/2. So they disagree with each other for many years. Okay, so that's an experiment. Okay. Besides the experiments, you can also do the numerical simulations. Okay. So here, I give you some very famous 2D or 3D numerical simulations. Okay. So actually, there are hundreds of such numerical simulations, direct numerical simulations in the leading journals. Some of them are from the Physics Review letter. Some of them are from the PNAS. Okay. Some of them from the JFM. Okay, so 2D or 3D, okay, simulation. You write a code and send that to user. You can run that in your own computer or in the HPC. Okay, but as real number goes to large regime, so the simulation is very expensive. Okay, usually the current direct numerical simulations generally is below 10 to the 14 in the 3D wide domain. Okay, and at the large real number, the flow becomes faster and faster, right? So your time step will be very small. Okay, to maintain the stability. Okay, and you need to run your simulation in long enough so to reach a statistically steady state. Okay, they are the challenges. Okay, so here I want to highlight some, the latest state-of-art 3D simulation. So they perform the simulation. Look at the date, 2025. Okay, they uploaded the manuscript this year. Probably they performed the simulation last year. Okay, so they are using the GPU simulation. Look at how many GPU they use. 3,300. Okay, so that's how many GPU memories? 107 terabytes. Okay, so what is the memory for your computer? Okay, so use so many GPUs and a large set GPU memories across 840 nodes supercomputer. Okay, and how many grid points? 46.7 billion grid points. Okay, so these run this simulation. I think these run that in 30 hours from their manuscript. Okay, and this is a 3D simulation. You can see as real number increase, the scale of the flow becomes finer and finer, right? And look, this is the largest value real number they reach. It's about 10 to the 12. 10 to the 12. It's far below 10 to the 25. All right. Okay. So that's what we can do today for the numerical simulations. Okay? All right. So these slides, I summarize the advantage and disadvantage of this series, laboratory experiments, and direct max simulations. So you can see, the challenge, there are still many challenges. Okay. So what we can do here, we're poor scientists at NYT, right? We don't have so many GPU nodes, right? Okay. All right. So what we can do? So we use a new direction. Okay. Instead of relying on the turbulent states you observed from the simulation, we compute the exact solutions, which satisfy the governing equation, the governing PD. Okay, the exact solutions, it could be steady state solution, it could be time periodic solution, it could be the traveling wave solution in fluid dynamics. Okay, this solution we call that exact coherent states. Okay, generally they're dynamically unstable. Okay, this is why if you run your simulation, you cannot obtain the exact solution at a large real number because the dynamics is so unstable. Okay, the flow is so unstable. Okay, we focus on the steady state solution because this is the simplest one. Okay, so this is some advantage. But here I want to discuss the challenge for computing the steady state solution because there's no free lunch. There's no free lunch. So the first challenge is these exact solutions, they are generally dynamically unstable. What does the dynamically unstable mean? So look at this graph. You can see if you put a ball onto this curve, the equilibrium state, that's unstable, right? If you give it some perturbation, it will be unstable. Okay, so that's the flow is same thing. Okay, the flow, the solution is there, exists, but due to some noise, due to some perturbation, it's unstable. If you run the simulation, it's unstable. Okay. Secondly, you can compute this kind of solution to 10 to the 19 or higher, but that's a finite real number value. How do you know your solution is this property also holds as real number goes to the infinity? That requires some theory. We use a asymptotic analysis theory. Okay, and then we can derive some scaling as real number goes to infinity. Okay, that's a motivation. Okay, so in the next part, I will briefly talk about the numerical method we developed and the theory we used to predict this asymptotic scaling. Okay, so maybe you will ask why you are interested in the steady state solution. So let's compare some steady state solution with a numerical simulation. On the top, they are the numerical simulation results. Okay, so this is the turbulent convection between no split boundary. This is a turbulent convection between stratospheric boundary. Okay, you can see. So here below are some steady solution I computed. Okay, you can see our steady state solution share many features of the turbulent convection. Okay, for example, this one. So you can see there's thermal boundary layers, very thin thermal boundary layer near the wall. Okay, there is a recirculation zone, separation zone here. Okay, and the interior is a large scale recirculation. okay, large scale role in the interior. So these exact coherent states, they comprise the backbone of the turbulent convection. Okay. All right. The first computation of the steady state solution was done by our friend Baole, who is from the University of Wisconsin. Okay, he did that 10 years ago. Okay, here is a strategy. He computes a steady state solution. He used some Jacobian-free Newton-Gemini solver, and then for fixed real number, he computes the steady state solution, and then he varies the aspect ratio. You can see some solution, the aspect ratio is large. Some solution, the aspect ratio is small. Okay, they vary the aspect ratio, and then he try to find the solution which maximize the heat transport. Okay, here is his result. He finds that the solution which maximize the heat transport, the heat flux is proportional to real number to the 0.31. Okay, and if you fix the aspect ratio, if you fix that and let real number go to infinity, he finds that the heat flux is proportional to real number to the 0.28. Okay, however, his computation is below real number 10 to the 9. So his result is not asymptotic. Okay. So next, for my work, it's about, I think this work was done 5 years ago. Okay. We developed a new algorithm, okay, and push computations up to 10 to the 40, 10 years ago. Currently, we can push that to higher real number. Okay, so we perform the computation in the string function verticity formulation. Okay, here is a PDE in verticity form, and so theta is equal to the temperature minus the conduction state. Okay, so this is the boundary conditions for theta psi is a string function. Okay, you can see, for this PDE, to solve this PDE, we don't have the boundary condition for the verticity. Instead, we have the boundary conditions for the string function. Okay, one strategy is you can put this verticity. You can substitute this verticity into the verticity equation. Then it's a fourth order, a fourth order PDE for the string function. However, solving a fourth order PDE, the stiffness is very high. Okay, so that will prevent you going to the higher, very large real number. Okay, so what I do is, okay, I solve the 3 second order PDEs. Okay, but since we don't have the boundary condition for verticity, but here we construct some approximate boundary condition, for the verticity field. Okay, so what we use a Taylor series expansion to build these approximate boundary conditions. Okay, as you know, in our numerical analysis class, we use the Taylor series, expansion a lot, right? We use that to construct many, famous algorithms. For example, the Newton's iteration, and the Runge-Kutta method. That's from the Taylor expansion, actually. Okay. All right. So with this boundary condition, we can solve these 3 second order PDEs. The stiffness is much lower. Okay. Since the steady state is unstable, so you must solve this iteratively. Okay, we use Newton's method. Okay, again, Newton's method. In the numerical analysis class, we use the Newton's method to compute the root of the nonlinear equation, one variable nonlinear equation. Here, we just extend this method to high dimensional PDEs. Okay, so from the Newton's method, you can derive some large-scale linear system, AX equals B. So here, delta F, that's a Jacobian matrix. So the delta X, that's an unknown. Okay, and this is a this is a vector, is a ratio of this kind of equation. Okay, So this is a large-scale linear system because in our fluid dynamic system you may have 1 million variables. So the metric could be 1 million by 1 million. So it's impossible. It requires a large side of memory to solve this directly. Okay. What you can do is you can solve this large-scale linear system using some iterative method. Again, the GMRS method. You will learn that from the numerical linear algebra. Okay. And then we use a spectral method. Horizontally we use a Fourier series because it's periodic. Okay. Vertically we use Chebyshev method. Okay. Fourier series we learned that in PD class. We did some Fourier analysis. Okay. All right. So here is a result at real number 10⁹, Prandtl number equaling 1. Okay, so I compute the steady states and I vary the aspect ratio. You can see the part A, the aspect ratio is 2, it's fixed 2. And you can see, this is a Newton number as a function of the 1 over 2 pi over gamma. Okay, so you can see 2 peaks. So the blue dots, that's a global optimal. Okay, so the part B. This one, the part C, that's a local optimal state. Okay, so this is the real number 10⁹. Then we push the computations to a higher real number. So you can see we compute these 3 types of solutions. The first one, the gamma is fixed 2. The second one, at a higher real number, we compute many points, and then we find the global optimal, and we also find the local optimal. Okay. So next, I will show you. Okay, most computations are were performed in this MacBook. Okay. So due to the efficient algorithm. Okay. All right. Then in this slide, I show some results. Remember these three steady solutions, okay, with different aspect ratios. So you can see this one, the gamma is fixed at 2. The heat flux is proportional to the real number a quarter. Okay, so the global optimal, the blue dot, the Newton number is proportional to real number 0.33. What's that? That's close to 1/3, right? So the last one, the locally optimal state, is proportional to real number to the 0.29. Okay, so these results, they are the first clear asymptotic scalings for really linear convection between no slip boundaries. Okay. All right. Okay, so now let's compare our globally optimal states. Let's compare that with the turbulent convection. You have seen the movie, it's turbulent convection, right? If we compare the heat transport, what do you expect? So which one is more efficient? The steady state, the optimal steady state, and the turbulent convection. Which one is you expect is more efficient? Which one? I think steady state. Okay. Probably you are smarter than me. Okay. So we all know that we know turbulent convection. What is turbulent? Turbulent try to maximize the heat transport. That's what we learned before, right? So say it again. What do you expect? Okay, thank you. All right. So this answer, he said turbulent convection will outperform the steady state. Let's see what happened. Okay. So you can see here is a 2D and 3D, simulation results, and some of them are experimental results. Okay. So they're all turbulent when real number is high. Okay. As you can see that our optimal steady states outperform all the turbulent convection data. Okay, so this optimal steady state is more efficient than this turbulent convection. Okay, so we perform these computations up to really to the 14. Okay, but that's not enough. how do you know your solution also, it's also valid as real number goes to infinity? How do you know that? So that requires the asymptotic analysis. Okay, so we, just remind you, we have these three types of solutions. Okay, we perform the asymptotic analysis for these locally observable states. Okay, so you can see this locally observable states is tall and thin, right? It's very tall and it's, the thin plume. Okay, so which means the horizontal gradient may be large. So we need to rescale the domain. Okay, here we rescale the domain and make it order 1, and then we derive the governing equation. This is the full governing equations without approximation. We just rescale the horizontal domain. Okay, and so for asymptotic analysis, actually, first of all, we need to gain some insights from the numerical solution, because the flow sometimes is so complicated. The physics is very complicated. Okay, so here is our numerical data. Okay, you can see this numerical solution is satisfies some symmetries. Okay, satisfies the horizontally the refraction symmetry, and also satisfies some central symmetry. So you just need to pay attention to a quarter of this flow cell. Okay, so we perform the I don't know why it's not very clear.
That's all right.
Okay.
Yeah, we don't blame you.
It's very clear on my computer.
Yeah, it happened to me one of them too, don't worry.
Okay, so this our numerical data suggests this solution satisfy the vertically four-layer structure. Okay, so you have a thin inner boundary layer that is a thermal boundary layer, and then you have middle boundary layer, outer boundary layer, and the core. Okay, so for the asymptotic analysis, generally for each region, they have different dominant physics. For example, in the core, since it's a thin plume, right? The horizontal diffusion dominates the vertical diffusion. Okay, so the vertical diffusion is relatively smaller. Okay, in the thermal boundary layer, the vertical diffusion is much higher. It go to the dominant term. Okay, so for each region, we find the dominant term and we balance them, and you can derive some reduced equations. Okay, and then so in the core, we can solve the reduced equation to find the analytical solution in the interior. Okay, so this is the core. So we apply the same strategy to the outer boundary layer, to the middle and the inner boundary layer. And then we match the heat flux and the string function across the different regions. Then we have a scaling. Here is our prediction. So we derive that the boundary layer here's the inner boundary layer is proportional to real number to a negative 3/10. Okay, and here are the scalings in different regions. Okay, so they are crazy. So how do you know they are correct? You must verify that using your numerical data, right? So here we perform our computations up to 10 to the 19. Okay, and then we compute that at real number 10 to the 17, 10 to the 18, and 10 to the 19. And then we rescale the flow field for each region. We just use this result, rescale that. If your scaling is correct, all the data will collapse. Okay? So you can see these three data, they collect very well. Okay? So which verify our prediction. Okay? All right, at the end of this talk, I will briefly talk about the research-based undergraduate curriculum built in our applied and computational math. Okay. So I joined NYIT at 2022. Okay, during the 3 years, we have developed a structured, step-by-step undergraduate training plan. Okay, to engage the undergraduate to our research. Okay. So here you can see we have 4 steps. step one, if this is your, year one or year two, don't worry about that. Just take the calculus, take the differential equation, and try to get an A. Okay. In your third year, so you will enroll in some advanced mathematics courses. For example, the PDE course, the numerical linear algebra, the numerical analysis, or mathematical fluid dynamics. So these advanced courses, they're generally project-based courses. Okay, so you will do some project with your instructor. Okay, not with your partners. Okay, and then you can see, so you can present your projects in your seminar, in math physics seminar, in the math day. Okay, that's a third year. Okay, the advanced course. So next, step three. Step three, some of the students from advanced courses, they express their interest with the professor. Okay, I'm interested in your research. Can I join your group? Okay, then you may be mentored by some professor. Okay, I know Dae-san, expressed his interest in a PDE class. That's why he joined my group. Okay, and then he will do some hands-on research in numerically using the numerical solver I developed, or use some software. Okay, but he will perform some simulations, and he will analyze the large size data, and finally we try to write a paper and for publication. Okay, and finally step 4. So once you have this result, you finish some projects, you did some research with the professor, the student will present their work in the NYIT Math Day. Okay, where many some local college and high school students, they will join this Math Day and share their research. Try to connect the math to real world applications. Okay, this is a paper learn to engage the undergraduates to the research in math. Okay. All right. Here is an example for my mathematical fluid dynamics course. So this is the syllabus I'm using for the fall 2025. Okay. You can see we have 3 parts. Okay. The part 1, I will assign some reading assignments, some lecture notes, some papers to the students. They read that after class, and then during the class time, we will try to derive that on the boards. Okay, the assignment is weekly. Okay, and besides that, we have 4 mini projects. Okay. Which provides research-oriented experience in thermal convection. Since I'm working on my research is focused on thermal convection, so this is mostly connected to thermal convection. So you can see this part ABC. Actually, this part ABC, they help the students build some foundations. For example, how to derive the Navier-Stokes equation and how to derive the advection, the Bose-Navier-Stokes equation. Okay, how to perform the linear stability analysis for the conduction state, and how to set up some numerical simulation. Okay, so this ABC, they have been done, but they help the student prepare for the higher level research. The part D is one part of my research. It's still an open question, so the student will work together on the part D, and finally they will prepare a paper. Okay, our goal is send this out for publication finally. Okay. Here are some pictures, some presentations from my OD, PD, and numerical analysis classes. Okay. So here, Michael and David, they talk about they use some OD model to predict the oil spill transport. Okay. Dae-san and Kale, they talk about some Gibbs phenomena using the Fourier analysis for the for wave equation, and this one this handsome guy, Abdul, he presents his research with me in the NYT Math Day. He performs some computations for infinite prime number, and he finds some new results. We are preparing a manuscript, and by the way, we will present this work in an international conference in November. Okay. All right. So you can see from my talk, I talk about the Newton's method, right? Some Fourier analysis, some other mathematical tools. Actually, they are very useful for the research, not only for the best. Okay. So you can see in our math major, this is the core courses we provide. Okay, with this course, they open a pathway to your career in different fields. For example, in data science, in finance. One student from the math major, she found a job in the Citibank, finance. Okay, and engineering and research and beyond. Okay. All right. So as I know, most undergraduate math researchers, they are supported by different grants. For example, the ISRC internal grants, the CES grants from the Dean's Office for summer, okay? And some external grants, for example, some Air Force grants and ASF grants, okay? So this grant, it means you are paid, okay? We mentor you to do some research and you are also paid. Is that good? Okay. So if you want to build a problem solving and computational skills through the undergraduate research, what should you do? What should you do? I know some of you have done that, okay? Enroll in the math minor, okay? Our major, okay? And connect with our math faculty, okay? All right. So at the end, I want to acknowledge the support from the Dean's Office, okay? The current and the former Dean, they give me a lot of support for the computing results for the travel grants, okay? I will acknowledge the support also from the math department, our chair, Dr. Roger Roy, and John. John gave me many instructions for my grant application, okay? Before this year, my SF grant was declined for several times. Okay, with John's instruction, this year I submitted 2 applications. Both of them were approved. However, I need to decline one because I cannot hold both of them. Okay, this is the first time I decline one grant. Okay, all right. And I was also thanks the other Anna, thank you for coming. And thank you for your support for my reappointment. Okay. I'm so glad to work with you in the math department. Okay. Thank you so much. Okay, so I will stop here. Thank you again for your attention. Thank you, William, for organizing this event. Thank you.
So thank you, Baole. That was a great talk.
Do you have all these that you can send?
Sure. I can share that with you. Yeah, so it seems that in this computer, the picture is not very clear. So in my computer,
I think when we record the recording, we'll have the higher quality images of it. It'll probably be what it sees on your screen. Yeah. Okay. Why it has that. So when you give a talk, something like this always.
Yeah.
That's great. Do we have any questions for Baole? I have a couple actually. So these steady state solutions, I think they seem a little bit like modes of the system, right? Like the normal modes almost, right? So are the turbulent solutions somehow like sums of like linear combinations of these normal?
That's a fantastic question, William. That's a fantastic question. Actually, since if you here, I think this these plots here.
Yeah.
So the phase space, right? In the phase space, there are many exact solutions. For example, there are many steady state solutions. They may have different aspect ratio. Okay, there are many time periodic solutions in the phase space.
Mhm.
In the steady state solutions, there's a fixed point, right?
Yeah.
Fixed point. Okay, so what is the turbulence? The turbulence in the phase space, if you draw the phase space of the turbulence, so the turbulence just travel around. Yeah, travel around these, exact solutions.
Never cut.
Because these solutions, they are dynamically unstable, but they're only unstable in certain directions. So the turbulent state, for example, it travel around a fixed point, a steady state solution a while. And then because it's unstable, it goes away. It's attracted by a time periodic solution.
Never reaches this.
Not it won't converge to the exact solution because they are dynamically unstable. So these exact solutions, they comprise the backbone of the turbulent convection.
Yeah. Partly.
Yeah. Thank you.
And is there like, so this seems like a really, great way to do it, right? Is there a reason no one had like, because it's computationally acceptable? Is there a reason no one really took this approach before?
Okay, so here, this is the first computation. So, but most of the people, they focus on the simulation.
Yeah.
Numerical simulation. Okay, you can use you can time integrate the equation and do some simulation.
Yeah.
That's easy, right? But so because that's easy to perform the simulation. But as I said, for the exact solutions, they're dynamically unstable. You need to use some advanced numerical algorithm to find them. You need to use a Newton's iteration. Okay, I know many many reviewers, they always mix the simulation and the computations of the exact solution. They are different. Okay, so the computation here, we use a Newton iteration to and find iteratively find the solution.
Yeah. Okay.
Yeah.
So the beta value that you got, were you saying that it works for the simulation?
Okay. Yes. Very nice question. The beta value. So you can see we have 3 betas. They are corresponding to different different types of the steady state solution. Okay. Here we compare this is our optimal steady state. The beta is 1/3. It's close to 1/3. Look at the numerical simulation data. You can see they have the very similar trend. Okay, so look, the vertical axis, that's the Newton number over is rescaled by really to the 1/3. If it reaches the 1/3, it will turn flat. Okay, so you can see all the data is there. As real number increase, it turns to flat. Okay, which suggests the 1/3 scaling. Yeah, but the steady state data, the heat flux is higher than the turbulent convection. Okay, it's more efficient the turbulent convection. Thank you.
All right. Well,
Yeah.
thank you. Let me close out.
Yeah.
All right. So again, thank you all for coming. I thank you all online for staying with us. So this concludes our first talk. And before we go, we have a little parting gift for Baole for being our first. There's something small courtesy of the dean.
Okay, thank you so much.
Show it to the camera.
This is the first in-person talk, I think.
Yeah, first in-person talk. So we've got courtesy of the dean, we got a little gifts for our speakers. So thank you for participating.
Thank you.
And we'll be having another talk hopefully in on October 2nd, I believe is our next date. So stay tuned, look for some advertising. We'll be sending some emails, and if you know anyone who wants to give a talk or who should give a talk and needs a little bit of a nudge, please go ahead and do such a thing. Anyway, we'll see. Thank you again, and we'll see you next time.
Yeah. Bye-bye.
All right. Bye.